Hey everybody, Mrs. Vaughn here. Today we're going to be talking about Hess's law and our continuation of talking about energy and heat. So we use Hess's law to really figure out what's the total enthalpy change of a reaction. So we use this whenever it doesn't really make sense to do a calorimetry experiment, or if it doesn't really matter what the exact numbers are, if an approximation is close enough. So for example, we're going to try and determine our enthalpy change of the reaction where we have sulfur combining with oxygen to produce sulfur trioxide. So we're looking at this combustion reaction. So we know that this has multiple steps. So in the first step, we have sulfur and oxygen combine to produce sulfur dioxide. And we also know that sulfur trioxide decomposes into this sulfur dioxide and oxygen. So these are things that we do know about these enthalpy changes. So we're going to combine what we know about a couple steps, a set of reactions to figure out our overall. Now I've highlighted the coefficients here because remember, enthalpy is based on moles. This is a molar enthalpy. So I have to make sure my number of moles match the equations that I'm using. This is really important. So we see that we have two sulfurs in our final equation that we're looking to solve. So since I only have one here, I'm going to multiply this entire equation by 2. And remember, delta H is included as part of that equation. So I'm going to multiply it by 2 also. So that should take care of the first piece for us. The other side, in the second equation that we're given, sulfur trioxide is listed as a reactant. But in our final equation, it's listed as a product. So we're going to have to flip this. Remember, when we reverse an equation from your notes, you have to also reverse or switch the sign of delta H. So since we're switching sides, we have to switch from our positive here. We're going to make that negative. So we're going to make this negative when we switch our reactants and products. Now we're going to combine these two equations. If you remember working with our spectator ions, hopefully you remember that if we have something on both the product side and the reactant side, we can cancel it out, just like if we had something in the top or the bottom when we were doing dimensional analysis. So since I have the sulfur dioxide, I have this 2, so it's different from this one because it has a different number, remember that. So since I have it on both my product and my reactant side, I can cancel that out. So now we're going to add, I don't see anything else that is on opposite sides. So now we're going to take and we're going to literally just add everything together. So I don't have any more sulfur, so it's going to stay the same. I have 2 moles of oxygen in the top equation. I have 1 in the bottom equation, so 2 plus 1 is 3. I don't have any sulfur trioxide in my top, but I have 2 in the bottom. So I have 2, 3, 2. That matches the mole ratio of the reaction that we're looking for. So I know that this is good. So now all I have to do is I just have to take my delta H and add those together also. So this is my final answer. Delta H is going to equal negative 792 kilojoules. If you have any questions, please feel free to reach out. Otherwise, thank you for watching, and I hope this was helpful.